All right, this is the 2003 free response question for intermolecular forces from the released AP exam. This is a short answer question, so most likely from the second half of the test when you are not allowed to use a calculator. If you haven't worked this problem on your own yet, I highly recommend that you stop or pause this video, go and do the problem yourself. See what you go on your own. Come back and let's see where you get some points. So I'll take a moment. All right, so first off, coming across the question, we have no data tables and nothing to go off of, so we're just going to go right into it. For each of the following, use appropriate chemical principles to explain the observation. Includes chemical equations as appropriate. In areas affected by acid rain, statues and structures made of limestone, which is calcium carbonate, often show signs of considerable deterioration. So what's happening here? I have acid rain, so some acid, and calcium carbonate. Now, any baby chem kid could probably tell you, oh, it's going to be a double replacement reaction. I'm going to end up with H2CO3 and calcium and some anion. And that baby chem student is actually on the right track, but you as AP chemistry students know there's no such thing as carbonic acid. It decomposes instantaneously into carbon dioxide and water. So what's happening here? Well, the statues are decomposing. So the acid in acid rain reacts with the calcium carbonate to reduce water, soluble salt, and a soluble salt and a gas. Therefore, eroding it. All right, so acid and acid rain, well, that's kind of redundant. What about the acid and acid rain? It's not just like, oh, acid, done. No, acid, it's the hydrogen. A hydrogen ion in acid rain. Okay, that sounds a little bit better. Now I'm not just being redundant. The acid and acid rain, that's what makes sense. The hydrogen acid rain reacts with the calcium carbonate to produce water, a soluble salt, and a gas, and therefore eroding the statue. I guess I should say the statue. Statue. There we go. Okay, so for this question is worth 2 possible points. You receive 1 point for pointing out that it's the hydrogen in the acid rain, or that acid rain has a high hydrogen concentration, and 1 point for pointing out that it produces gaseous carbon dioxide. Why they didn't want the rest of it, I don't know, but the rubric says 1 point for indicating calcium carbonate solid forms gaseous carbon dioxide. You don't need to see that. There we go. Table salt and sugar are dissolved in water. It is observed that both solutions have a higher boiling point than pure water. Okay, so what's going on here? This is another question that you could probably get from a pre-AP student. They would know, okay, well, there are colligative properties. That's all change based on not what you dissolve into solution, but how many particles you get from that thing that you dissolve. So when both are dissolved in water, what are they doing? Well, they raise the boiling point. Now, any pre-AP student could probably tell me, oh, it's because of colligative properties, they're going to raise the boiling point. You, as an AP student, go, well, there's more to it than that. So what about boiling point? Why is the boiling point changing? Well, things boil when their vapor pressure is greater than atmospheric pressure. Atmospheric. So when the vapor pressure of this these two solutions is greater than atmospheric pressure, the substance boils. So what must be happening here? Well, the vapor pressure of the solution must be lower. Than the vapor pressure of, what would you call water by itself? Let's say of a pure substance. In this case, we're talking about the water. Since substance boils when its vapor pressure is greater than atmospheric pressure, I guess I shouldn't abbreviate too much. Solution has a higher boiling point. This is one of those questions where there's some overlap between two units. This combines our solutions unit as well as our intermolecular forces unit. What's effectively happening here is that you have some compound in this water that you remember that vapor pressure is exerted by water molecules that absorb on the surface that are attracted by less by the waters around them than molecules inside, which are attracted by molecules all around them. Those intermolecular forces are slightly less on the surface, and so those water molecules escape into being a vapor, but they don't gain very much energy and they exert the pressure on the surface of the water. When you add a salt or another compound, those molecules or those particles from that solute disrupt or take up space on the surface, and now there's less space for these water molecules to absorb that energy and escape. And so vapor pressure is less for a solution. So however you went about describing that, maybe with a picture, but you had to talk about it in some way. You can't just draw a picture and expect them to know what you're thinking. It's in ancient Egypt, no hieroglyphics. Got to explain it somehow. You got 1 point for this question. So you got 1 point for pointing out that the vapor pressure of the solution is lower for a solution than it is for a pure substance, and somehow relating that back to the boiling point. So the next question says, okay, well, the boiling point's lower for both of them. Or sorry, it's higher for both of them. But why is the boiling point higher for sodium chloride than it is for table salt? So depending on how you learn this in baby chemistry will depend on how you answered the question. Now I know in my baby chem class, I learned the formula delta T equals M dFK, where M is the molality, or some form of concentration. Usually we did moles, or molality is moles per kilogram of solution. Let's make that a little cleaner. Come on, moles per kilogram. There we go. dF is dissociation factor, and K was some constant. And this change in temperature depicted how high boiling point would rise, so plus for boiling point, and it was always you subtracted it for freezing point. So you subtracted it from the normal freezing point if you're doing freezing point, you added it to the normal boiling point if you were doing boiling point. So that's how I teach it to my baby chem kids. And this dF stands for how many ions you get in solution. Now, if you are in AP and your teacher has already gone over solutions, you know the formula delta T equals MKI, where I is the same thing as dF, and maybe you might even know the fancy word for it. It's Van't Hoff. Named after Louis Van't Hoff, the chemist who did a lot of experiments with colligative properties. I believe it's Lewis. If it's not, someone can yell at me later. So if the concentration values are the same, and it's the same solution that they're in the same solute, or sorry, they're in the same solvent, that K is going to be the same. The thing that's changing, therefore, has to be this I, this Van't Hoff factor, or in baby chem, the DF. So, what do we know? I, Van't Hoff factor. It's how many particles you get in solution. So if I take sodium chloride is highly soluble because I have a halogen that's not paired with silver, mercury, or lead, and I have a group 1 metal. Very few exceptions to group 1 metals are soluble. So sodium chloride is extremely soluble. And then I have C12H22O11. I have sugar. I put sugar in water, I still have sugar. Covalent compounds, or non-electrolytes, don't dissolve in solution. So the Van't Hoff factor for sodium chloride is 2. The Van't Hoff factor for sugar is only 1. So the boiling point of sodium chloride, assuming they have the same concentration, and they do, is always going to be higher than the boiling point of a solution of sugar. So now we just need to explain that. So sodium chloride as a Van't, there's a T here, Van't Hoff factor of 2, while sugar is a Van't, has an awful F. Now it's an A. That makes sense. Erase. Oh god, these pens are too big. Factor of 1. Therefore, delta T equals mki if I is 2, it will be a greater change in temp for sodium chloride. Then if I is 1 for, what was it, 12? Sugar. All right, for this question, all of that was worth only 1 point. Kind of disappointing, because questions are worth different amounts, no matter if it takes you 20 minutes or if it takes you 2 seconds. Sometimes they're worth very little, sometimes they're worth a lot. This question, only worth 1 point. You got 1.4, pointing out that sodium chloride forms 2 particles and sugar only forms 1 in solution. You can even say moles of particles because it's the same thing. Letter C is another question that delves into other units that we haven't talked about in a little while. The gas laws. It says methane does not behave like an ideal gas at low temperatures and high pressures. So what's happening here? Okay, so I have a container of methane, and I'll just put the C's. I have a bunch of methane molecules. At high temperatures, they're bouncing around really fast. And because of that, they behave like ideal gases because there's not enough time, even though time is relative, there's not enough, they don't come close enough for their intermolecular forces to matter. So the intermolecular forces are 0, which is one of the postulates of being an ideal gas. You have no attractive forces. At the same time, we know that gases behave more ideally at low pressures because they're very far apart. And I gotta see here, methane there, but there's a lot of distance between them. Their volume that the gas takes up is much bigger than the volume of the gas. At high pressures, that volume the gas takes up is going to start to become important. So at high temperatures, at low temperatures and high pressures, two statements or two postulates of the kinetic molecular theory are violated. First off, at low temperatures, at low temps, the intermolecular forces are not zero. At low temperature, intermolecular forces, which are LDFs, in case we're going to be graded on that, London dispersion forces are stronger. Well, that's not a good statement either. Let's go with our more attractive because the gas has less kinetic energy. At high pressures, gas volume, the system's volume is small. And the volume of the gas becomes more important. Therefore, violating two of, I'm going to be off the screen, the postulates of the kinetic molecular theory, and thus being, scroll down, a real gas. Whew. So again, this question's kind of hovering between 2 units, or well, 3 units with this question. But if you're able to remember all of that, this question's worth 2 possible points. You got 1 point for talking how intermolecular forces become more important or more attractive with less kinetic energy. And you got 1 point for talking about how the volume decreased and therefore the volume of the gas becomes a bigger issue. Last one. Water droplets form on the outside of a beaker containing an ice bag. So this, I live in the South. I live in Virginia, in case you are watching this online. And in Virginia, specifically in the summer, when we get a glass of sweet tea, it comes in a mason jar and it never fails. Halfway through drinking your glass, you need a coaster because your glass starts to sweat. Some of the people in Virginia might go, oh, well, it's because my glass must be leaky. But no, it's not. It's not because you're losing water or sweet tea from the outside, from the inside of the glass. The water molecules outside are contacting the edge of that glass, depositing energy and turning back into their liquid phase because there's always moisture in the air, especially down here in the tidewater area next to the ocean. We have lots of moisture. So we've got to talk about how this is really just a phase change. moisture in the air contacts the glass beaker, loses energy and condenses back into a liquid. And we might want to point out, we know that this is moisture in the air, this is water, the gas, and hopefully your grader will be able to read your handwriting because that's a little shady over there. And this is water, the liquid. All right, this question, I believe, is worth 2 possible points. You got 1 point for pointing out that it's water in the air, so moisture in the air, and 1 point for talking about it losing energy and condensing. Another route to go about this would be to go through vapor pressure, in which case you would get 1 point for indicating that condensation occurs because the equilibrium vapor pressure at the temperature on the surface of the glass is lower than the pressure due to the water vapor in the air in the room. If you went that route, you're smarter than me. I just like saying, okay, it's moisture in the air, loses energy, condenses back into a liquid. Pretty simple. All right, so remember, you do not need to get every single question right in order to get a 5. Oh, as my voice cracks. You only need to get half of the points. So this question was out of 2, 3, 4, 5, 6, 7, 8. So if you got 4 out of 8 points, you are doing very, very well, and you should pat yourself on the back, pat your teacher on the back, because you are well on the way to a 3, 4, or 5.